The topic of the video is scattering from a screened Coulomb potential. If a charged particle of charge Q2 is incident upon a neutral atom with a nuclear charge Q1, then the interaction potential energy can be written as V r prime is equals to Q1 Q2 divided by r prime into exponential minus r prime divided by A. And this is called a Screened Coulomb potential. The scattering amplitude for asymptotic region, that's after the Bond's approximation, and for the elastic scattering can be expressed as f is equals to minus 2 mu over h cut square q into the integral for r prime from the limits 0 to infinity, and then r prime into v of r prime into sine q r prime into dr prime. We can see that r prime will get cancelled here and here, and if you write these charges q1 q2 which are constants outside, then we have this integral left, and the integration for the exponential minus r prime divided by a into sine q r prime dr prime will be or q divided by q square plus 1 over a squared. So we can see the q here and here it will get cancelled. So and in place of q, if you substitute 2k or 2k into sine delta by 2, where delta is the angle between the vector k0 and then the vector k, then we can actually see the scattering amplitude as minus 2 mu by h cut square into q1 q2 divided by 4k squared sine delta by 2 plus 1 over a squared. And the differential scattering cross section, which is just the square of modulus of scattering amplitude f, can be written like this. And the total scattering cross section, which is the double integral of d sigma by d omega, the differential scattering cross section over the integrations theta from 0 to pi and then phi from 0 to 2 pi. And since this d sigma by d omega is independent of the coordinates theta or phi, then the stuff d sigma by d omega can be written as a constant outside the integrals, and then the integration over theta and pi will give us a factor of 4 pi. So we finally get the expression for the total scattering cross section like this. That's it in this video, and thanks for watching.